Information in a data structure is often stored as key value pairs. A value is all the information for something that you want to keep. For example, for a student, we may want to keep their name, their major, the courses they've taken, the grades in those courses, and so on. It's comparable to all the papers that you store inside a file folder. The key is something unique to that thing. In the case of a student, it might be their campus ID number or their social security number. It can be anything that can be used to search for that student without ambiguity. And in the context of the traditional paper folders, the key corresponds to what you write on the tabs. By the way, the key does not have to be a number. It can be anything like a string that represents their last name and first name, as long as it is unique to that particular student. Now, a data structure stores collections of key value pairs such that you give a key as input, and the data structure outputs the corresponding value. So in this example, the input is a student ID 7216, and the output is the corresponding record of only that student with that ID. Now, there are different ways of implementing a key value data structure, and one such is with a hash table. Hash tables have already been implemented in C++ as part of its standard library. The standard library calls it an unordered map. And if you're familiar with the map class in the C++ standard library, the usage is very similar. Right? To use a hash table, you first included the unordered map library. Then you construct an empty hash table. It's a templated class, which means that I need to give the type of the key and the type of the value. In this example, I created a hash table called GPA record, where the keys are going to be strings and the values are going to be doubles. Now I can add things into the hash table like so, GPA record, and then the key Alan within square brackets equals the value 3.42. I can add another key value pair. In this case, the key is Beth, and the value is 3.5. Now later, if I want to look up what is the value of Alan, I can print it to C out by calling GPA record and again giving Alan as the key in square brackets, and GPA record will now return to me the corresponding value and print it out. I can also remove a key and its corresponding value by calling the erase method again with the key. So notice that the use of square brackets is like that of an array or a vector, and the key acts like the index, except that the key does not have to be just a number. In fact, another name for a hash table is associative array. Now, there is one thing to watch out for, which is in C++, anytime you use a square bracket operator on a hash table with a key that is not present, it will automatically insert a default value. So ideally, before you look up a particular key, you want to make sure that that key actually exists. And the way you do that is by calling the find method. If the key does not exist, then find will return the end iterator, and you can check for that before trying to use the key. So this is shown in this if statement here, which calls a find and then compares it with the end iterator. Hash tables or unordered maps are fast, and often faster than even ordered maps, to get individual elements by their key. So next, we are going to look at how a hash table is able to provide this fast performance. You've probably seen other data structures that can store elements. For example, if I wanted to store 9 elements, I can store it in a linked list like so. But the worst case complexity of finding something becomes O of n, because in the worst case, you may have to go through every element in the linked list. Here, n refers to the number of elements already in the data structure. A better approach is to use balanced trees or the ordered map, in which case the worst case time to look up an element is much smaller, only O of log n. The reason is because you don't have to look at every element in the tree, only at the elements along one path from the root to a leaf. By the way, in all these pictures, I'm showing only the keys. You have to remember that every key also has an associated value, which I've just not shown here, just to keep the figures simple. Now, is it possible to come up with a data structure that has complexity even lower than log n, say O of 1, that is a constant time data structure. This would be pretty impressive because constant time means that it does not matter how many elements I have in my data structure, 10 elements or a million elements, the time to find an element would be about the same. As it turns out, the simple array can do that. I can just store key 1 in index 1, key 5 in index 5, and so on. And now if I want to access some elements, say the value 11, I can directly look at the cell at index 11 without going through the other cells. So this is constant time access. However, this has some pretty big disadvantages. One is that it requires our keys all to be integers. That is, they cannot be other types like strings. But more problematically, this array has to be as big as the largest key. This wastes a lot of space because the largest key can be very large, but I may not have that many elements. So the hash table is an attempt to reach a constant time data structure using an array, but not using keys directly as array indices. Instead, we will use some math to convert any key into an array index, a process called hashing. So specifically, a hash table consists of an array of size n and a mathematical function that converts a key into an index of this array. So this array is sometimes also called a hash table, which is where the name hash table comes from. And now the core idea is this: anytime I need to store an item with a key k, I will hash that key to get some array index shown here as h of k and store the item in that particular location. Now let's look at the process of hashing, that is converting a key into an index. Typically, this is implemented in two steps. The first step is we first apply a mathematical function called a hash function to convert the key to a very large number called the hash code. We'll next apply another mathematical function to compress this large hash code into a much smaller number, one that falls within the range of valid array indices. This second function is called a compression function. We'll focus first on the compression function, and we'll look at some hash functions later on. The simplest and most commonly used method to convert a hash code to an array index is just to divide it by the size of the array and use a remainder. This operation of taking the remainder is also called the modulus, the mod operator, and in many programming languages is represented by the percentage symbol. For example, if the size of the array is 7, and I want to get the array index of, say, key 20, I would do 20 mod 7, and that is dividing 20 by 7 gives me a remainder of 6, and then I would store the key 20 in index 6. Now that we know how to compress a number into an array index, let's see how we can insert data into a hash table. So let's say the size of my hash table is only 7, and let's say I want to insert these 3 keys into the hash table. We'll start with the first key, key 20. 20 should go into array index 6 because my compression function says get the remainder of dividing 20 by 7, and that is 6. The next key, 25, should go into index 4 because 25 mod 7 is 4. And similarly, the third key, 30, should go into array index 2 because 30 mod 7 is 2. Searching for a key is similar to inserting. For example, to find out if key 25 is in this hash table, I first calculate its index, which is 25 mod 7, and that is 4. So I'll directly look at the location at index 4 to get the corresponding value. Notice that I'm able to do this in exactly 2 steps. First, calculating the index, and second, looking at one array location. So far, searching and inserting can be done in constant time. But now let's try to insert a 4th value, let's say 16. Well, 16 should go into array index 2 because 16 mod 7 is also 2. But look, there is already something there in that location, and we should not overwrite that value. This is called a collision. So a collision happens when 2 different keys get assigned to the same table index. So many different numbers, when divided by 7, will have the exact same remainder. And inserting any of these numbers as keys will cause collisions. So collisions are to be expected because the number of possible keys is so much larger than the size of any table. So notice that collision is not an error. And dealing with collisions is the main challenge when designing a hash table. So there are different approaches to deal with collisions, and some of them are listed here. And we'll next go over a couple of these. So the first approach to dealing with collisions is called chaining. The main idea here is that we do not store our keys directly in the array of the hash table. Instead, each element of the hash table now stores a bucket of keys. And this bucket can be implemented either as a linked list or as a vector of keys. Now, if I want to find a particular key in this data structure, I'll again calculate the index using hashing and then search in that indexes bucket for that particular key. I can also use a similar approach to insert new keys. I will hash the key to get the index and then insert it into that corresponding bucket. Removing a key is also similar. Okay. So here's an example. Let's say that this is my hash table. The hash table has size 13 and so 13 buckets. To insert key 23, I calculate its index, which is 23 mod 13, which is 10. And so I insert this key 23 into the bucket at array index 10. Right. Now let's look at the worst case performance of the chaining approach. The worst case happens when all the keys are assigned to the same bucket as shown here. So to find any key in such a hash table, I may have to go through every element in that single bucket. And the worst case complexity is therefore O of n. Inserting when duplicate keys are allowed can be done in O of 1 time because I can just add keys to the head of the linked list. However, if duplicate keys are not allowed, I'll again have to check every element in a bucket to see if that key already exists. And this is again O of n. Removing also has a worst case complexity of O of n because the key to be removed could be at the end of the list, and I'll have to go through every item before reaching the end. So you can see that the worst case performance looks pretty bad, but we'll soon see that the average case is much better than the worst case. But before we study this average case performance, let's look at another approach to preventing collisions, and that's called linear probing. So in linear probing, we go back to the idea of having a single array of keys, but when inserting a new key, if I find that if a particular space is occupied, I'm just going to look at locations next to it until I find an empty space and then insert it there. Our searches are going to be circular, which means that if I reach the end of the array, I'm just going to start looking from the beginning. This will become much clearer when you visualize it with some examples. Okay. So let's say I have a hash table of size 13, and I want to insert 10 keys. For simplicity, my keys are integers, which means that I can use a simple compression function of the key mod 13 to calculate the array index. These indices are also shown below the key. We'll first start with key 18. Key 18 on hashing should go into array index 5. And so that's where 18 goes. Next, let's insert key 41. 41 will get hashed to array index 2. So that's where it goes. Next, let's insert key 22. 22 on hashing will give me 9. And that's where it goes because location 9 is empty. Now let's try to insert key 44. 44 gets hashed to array index 5, but we already have a key at location 5, and we don't want to overwrite it. So we'll just insert our key 44 at the next location, which is index 6. Next, let's insert key 59. 59 gets hashed to index 7, and as that location is empty, we can just insert it there. Next, let's insert key 32, which gets hashed to 6. But there's something already at 6. So we look at the next location, and there's something there too. So we need to keep going forward until we find the empty location at 8. Now let's insert key 31, which gets hashed to index 5. So we start probing from 5, and we'll keep going forward until we find an empty space. Next, let's insert key 73. 73 gets hashed to 8. So we start probing from 8 until we find an empty location. So one thing you'll notice is that as the hash table gets filled, the keys start bunching up. And this will become important later on when we analyze this performance. Next, let's insert key 20, which gets hashed to index 7. So we start probing from there until we find the first empty space at location 12. Finally, let's insert key 49, which gets hashed to index 10. And so we start probing from there. But when we reach the right end of the array, we will just wrap around and start probing from index 0. As that space is empty, we will insert key 49 at index 0. We'll next start looking at some of the implementation details of linear probing. First, how do we represent an empty cell? Notice that in an array, every cell has to have some value, even if it is supposed to be empty. So we'll need some special marker to represent an empty cell. Let us call it E1. And initially, all our cells will have value E1. Now we can insert a key into a cell, and that value will marker will get replaced by the key. Now, if we later delete the key, this cell becomes empty, but this should not be replaced with E1, but with a different value E2. Okay. So we have two kinds of empty cells, because how a cell is empty, whether it was always empty or it became empty after a delete, will matter during a search, as we will study next. So we're going to start looking at some of the kind of code that is needed to implement these three main data structure operations of find, insert, and remove for a hash table. So the first operation that we'll study is finding a particular key in a hash table. Okay. The only input is some key k. And the first step is to calculate the corresponding index by calling the hash function shown here as h of k. So we start at that index and probe consecutive locations. And this sequence of probes is implemented here as this repeat until loop. These iterations will continue until one of the following occurs. We find the key, in which case we return the corresponding value, or we find an empty cell, which means that the key does not exist, and I just return that I don't find it. Okay, which means so we don't find it. Now note that our empty cells can have either of two values, but we should stop the search only if we reach E1, a cell that is always empty. Okay, and an empty cell with E2 becomes empty because of a delete. So the key that we are looking for could be present to the right of it, and so we should continue searching. So that is why we only stop if we see an E1. It's also possible that our table is full, and in which case we will not find an empty space. So we check for a full table by keeping a count of the number of probes or the number of iterations and exiting the loop when the count reaches the array size n. Okay. So the small variable n is our number of probes. By the way, notice this line here implements moving the index to the next location for the next iteration or probe. The mod n here does the wraparound to the beginning when the index reaches the end of the table, that's the size of the array. The second operation, insert, is similar. The inputs are the new key and the corresponding value. We again start from the hash value, which is given by the hashing of the key. But this time we'll start probing until we find the first empty cell. Okay. And it doesn't matter if it is E1 or E2, we can use any empty cell to store our new value. Okay. So once we find this, we store the corresponding key and value in this empty cell, and then we are done. And I'll keep probing in this repeat until loop until I find an empty space or until I realize that my hash table is full, which I check by keeping track of the number of probes in this variable small n. The third operation, remove, is also similar to find. The only input is some key k. And essentially, we repeat the same steps as in the find operation to get the cell that contains that key k. And then just we overwrite that cell with our E2 marker to indicate that the cell is now empty and I can reuse it in the future. Okay. Next, we will analyze the computational complexity of these operations. One of the things that you would have noticed is that collisions cause items to lump together, which means that as the table gets fuller, the cost of finding, inserting, or removing a particular item also increases. In the worst case, all the keys that I inserted can happen to collide, and they occupy one long continuous portion of the table. And now any new insert or find will require checking all of these keys one by one. And so the worst case complexity for all these three operations is O of n. While the worst case complexity is bad, the typical performance may not be that bad. It depends on how full is a hash table. How full a hash table is can be quantified by a number called the load factor, which is represented here by the symbol alpha. It is the number of items in the hash table, small n, divided by the total capacity of the array given by capital N. So alpha is a number that varies from 0 to 1. 0 means that the hash table is empty. 1 means that the hash table is full. So the performance or the cost of finding something in the hash table depends on alpha. Specifically, in the case of linear probing, and assuming that the hash values are like random numbers, the expected number of probes before I can do an insert is given by the formula 1 over 1 minus alpha. If you can see that as alpha increases, the number of probes increases rapidly. So the recommendation is to keep the load factor small. For example, if I keep alpha to less than 0.5, that is, I make sure that my hash table is only half full, then the expected number of probes becomes 1 over 1 minus 0.5, which is less than 2, which is a constant. So this is a big improvement compared to the worst case cost of O of n. But what happens as we keep adding items to the hash table and the load factor becomes higher than we would like? We can then create a new array of double the size and copy all the items from the original array to the new array. We'll need to compute the locations of all the items in the new array by rehashing all the keys, taking into account the size of the larger array. The old array can then be destroyed. So this process of creating a larger array and copying all the elements is called dynamic resizing and rehashing. This is a time-consuming operation, but does reduce the load factor by half. For example, consider this array of capacity 5 with 3 items. The load factor is 3 over 5. We can resize this array to an array with double the capacity, 10, and the load factor, and then we rehash all of the contents. And now notice that this reduces the load factor to 3 over 10, half of what we had earlier. So in practice, what all this means is that inserting and finding things in a hash table is very fast, provided my load factor is not close to 1. When the hash table is not very full, the average running time of all the operations is only O of 1. But to get this fast performance, hash table implementations typically keep the load factor less than 0.5 for linear probing and less than 0.9 for chaining. You might also wonder which approach is better, linear probing or chaining. There is not one answer. The conventional wisdom is that in modern cache-heavy architectures, linear probing is faster due to locality of reference. What this means is that when the processor fetches something from one location, one array location in the main memory, it automatically fetches everything close to it. This is great for linear probing because probing for values just to the right of a memory location becomes very fast. However, linear probing degrades badly when the load factor is high. So for some reason, you're not able to keep the load factor low. For example, you don't have much memory, you're working on an embedded system, then it's better to use chaining. So far, all the examples that we've seen had integer keys, but hashing can also be used when keys are not integers. For example, they can be characters or strings. All that we need is a hash function to convert these non-integer keys to numbers. So let's look at a few simple methods to hash some non-integer keys. In the case of characters, you may know that individual characters are represented inside a computer as a number that's given by the ASCII code. For example, the letter capital A is represented by the number 65, capital B with 66, and so on. And here is actually the full list of characters and the corresponding ASCII codes of this. So if my key is a character, it's simple. I'll just use the ASCII code as the numeric key. But what if my key is not a single character, but a string of characters? For strings, one simple approach is called taking the component sum, which is just adding up the individual ASCII values for each of the characters in the string. For example, for string A, the value is just 65. If my string is AB, I add the corresponding value, say 65 plus 66, which gives me an integer 131, and I can use as a key. Now, one approach with this is that the order of characters do not matter. For example, if I have two names, Ramon and Norma, they'll both have the same hash code, which means that if I insert these two keys into a hash table, they will collide. And we know that collisions degrade performance. So there are more complex approaches that try to reduce the chances that different strings will collide, but we'll not get into that in this presentation. Also, there are hashing functions for other types of keys. So we can store them in a hash table. But again, we won't go into those. So before I end, so let me summarize all the concepts that we went over. We started the concept of each data item having a key and a value. And this hash table is a data structure to store a set of these key value pairs using an array, also called a table, and a hashing function that converts any key into one array index where the item is stored. The main challenge with this approach is that different keys can get assigned to the same array index, which is called a collision. We looked at two different ways of dealing with collisions, chaining and linear probing. So both these approaches, the worst case cost of finding, inserting, or deleting items into a hash table is O of n. This is not impressive, but if we consider the average case, this is much better at O of 1, that is a constant time. Okay, so our initial goal of reaching a constant time data structure, was only partially realized. We could not reach constant time in the worst case, but only in the average case. But this average case performance happens only when the array is not very full, and this is measured by the load factor. As a table starts getting full, it is necessary to dynamically resize and rehash the contents to a large table to keep the load factor low. And finally, all of these details are hidden if you just use a C++ standard library's implementation of a hash table that's called an unordered map.